Welcome to the lecture series on object-oriented analysis and design. Just commenced the talk on the lecture on software reuse. Object-oriented analysis and design has not only promised to maximize the idea of software reuse, which has been spoken of. We have been talking about it: code quality, reentrant code, reusable code. These were ideas that were there in software for several decades. Object-oriented maximized that possibility. It was a very attractive idea, but then we were not able to scale. That's the reason why software reuse became intriguing. It was lying low for quite some time. Today the time is there, time is ripe, where we talk about existing code bases and then we want to put them together to make them better, to make them reusable, make it faster. The development must be faster. In the last lecture we have seen the idea about interoperability. Interoperability remains the key for building complex systems very fast. Hardware is promising. Hardware is very promising that it will create such possibilities. We talked about reconfigurable computing. We talked about what are called gate arrays. There will be so many things on the chip, you can quickly change the connections. We have talked about telephone switch, a great example. The hardware side of the telephone switch, it just makes the circuits faster. All telephones work. Now it's all software controlled. The telephone switches are also software controlled. They're all patented. But then the point is, we have seen the huge plus of that inflexible hardware which matured so fast that reuse and interoperability are just commonplace. What it is doing, it is dictating, saying that you must use this. As I mentioned, a simple example, the RC filter, only two variables are there. You vary the resistor or you vary the capacitance. It's up to you. If you choose both which are existing, then the equation is the same. It will just give the required result of an RC filter. So now coming back to the point, how do we do that in software is the question. It is very flexible. In the field of software, requirements driven, use case driven is proving to be very promising. So that is why we keep telling that in software system interoperability, the higher we start, we should plan for it. Very soon, then it becomes interoperable. Develop software with fewer people. Now that concern was also there. We need to talk about lean teams. We need to talk about clearly identified functionality of the teams. So these are certain puzzles which we try to address. Why? Because we want to take advantage of software reuse. It's an intrigue. It's a matter of intrigue that we could scale it very high, like the hardware market has scaled very high. Move personnel more easily from project to project. It's a luxury today. Even 15 years back it was a luxury. 15-20 years back it was a luxury that a team leader is leading only one project. At that point in time, things were even more stringent, that the team leader does not lead projects in the same facility. If they are leading 3 projects, each project will be in one facility. These were certain simple disciplines in which the people in the industry were working. This project happens in this facility, the physical facility. Other project happens in another physical facility. The gentleman who is leading the team or whoever is the team lead will have to move across those facilities based on some schedules. Many things were like that. Then they started building floors, access restrictions were there. There were so many, there's an ISO standard on how the personnel can move from project to project. So in all these cases we took recourse to software, that is simply saying that it is computer supported collaborative work. So today I am on 2 teams on a package. They are all independent, mutually independent. I get messages wherever they are. All one particular team has 100, another team has another 100 plus 150 people. They are all separate. The package is the same, but virtually they are separate. So when I am working with this team, all of us are in completely different virtual facility. When I am working in the other team, we are completely in a different virtual facility. There is no connection. So we have adhered to certain standard practices. It's very difficult to ask that question and then dig deeper into what is a guarantee that is happening like that. It is happening, that's all. There are so many things, so many conferences we are running on common packages. They are all running as virtual silos for us. That particular exercise is built like this. I can be in theory in multiple such facilities. In practice, it is believed that the software is assuring that. We build very trustworthy software, there is no cross current, there is no crisscross current, it happens. Reduce software development and maintenance costs, produce more standardized software, produce better quality software, and provide powerful competitive advantage. Where is the competitive advantage coming from? Is it coming from building a completely new application software which nobody thought? That is becoming rare. That used to be the case. If you want to have a competitive advantage, you should create a space of your own for that software. You should create a space for that software and tell that this is very unique. Things have changed. We know that there are commonalities, common things will happen. Today, most of the common activities are all done by Google Apps. It's all there. Whatever you want to do, it is there, it's free, it's open source. Well, the business dynamics is one, the restricted trade practices is another. We have so many things which have contributed to the business dynamics, and today what are we talking about? We want to talk about a business driven, requirements driven, use case driven complexity, and that is the reason why we are opening up in a much faster way for allowing code bases to be connected, for reuse to be connected, for service oriented architectures to thrive. That's another way of talking about the same idea. What is reusable? Entire application system. That's what I mentioned in the beginning of this set of lectures, that we have already brought several pieces of software, bought and brought several pieces of software into the organization over a steady pace of time. Putting together all these applications is a very big challenge. Integrating applications is a very big challenge. If one application developed by X talks to another application developed by Y, it's a great thing. So they are all there, they are all spread across the organization. Application integration is a very big challenge. So we should have some way. One promising idea was what is called service oriented architecture. There are two ways of doing it. One is the cloud, which has become very famous, very popular. The second one is web services. We simply put a wrapper around the application and tell that whoever has a way of connecting to this wrapper, that's a reuse idea, to this wrapper, you can connect with that application, get that small thing done and be done with it. The bigger application, nobody knows what it is doing. If you want this much, you take this much exercise. Subsystems. We can talk about various subsystems that are reusable, components, this I have spoken, modules, object, function and procedure. However, we think that maximum benefits for reuse come at a higher level because, as I began to tell, the business driven, that's the first step, that is the time when we should think of reuse. Therefore, at this larger end, we think that the return on investment will be promising. The lower end, yes, it can be reused, we can talk about it, there is no reason why we can't, but then the return on investment or being business wise doesn't happen really at this lower end. It happens at the higher end, application and subsystem. Reuse based software engineering. For a spell of time, we were talking about highlighting what is different in the software engineering. We started talking about software engineering first as traditional software engineering. Then we moved to object-oriented software engineering. Books were written, OOSE. OOSE is an object-oriented method. It began to be well known as an object-oriented method created by Ivar Jacobson. One was private, one was public and open. So we used use cases. His idea of use cases has been very prominent. We talk about everything as use cases. Now the next idea in software engineering, reuse based. But please remember, we need to understand that software engineering is very much there. It is not completely altered, nothing revolutionary happened. All those nice concepts which were stable by 85, practices by 90, the changeover to quality as the top rung topic through a process based project management, systems use by 2010, all these are retained. However, we make it very, very clear to have reuse-based software engineering. There have been a few which were very nicely into research. As I said, one was the object-oriented software engineering, reuse-based software engineering, aspect-oriented software engineering. The software engineering began to get accentuated using some flavor like this: aspect-oriented, reuse-based, and so on. System reuse, application reuse, component reuse, object and function reuse. So we think that a software engineering from step 1 that proactively looks for what can be reused at a higher level is going to help us. Where there is a reuse possible, let it dictate. Like the hardware component market was dictating us, saying that there is no capacitance of this value, please change the value of the capacitance. The market is not supplying that. Something happened, it is not supplying. So please change the capacitance value. You work out on the resistor, it's just 2 parameters, we are toying around with variable parameters. So we said that if we plan ahead, the business development starts looking at what we have, what we are looking at. There is no point in reinventing the wheel, let it dictate. The process, the life cycle, everything is dictated by the reuse potential possible, which is perceived very early. And what is that paradigm that is making us perceive that very early? The object-oriented paradigm. System reuse, application reuse, component reuse. Up to that, it is proven to be reasonably good on return on investment. Object and function reuse, it's good, it's nice to talk about, but that's in toy projects. Software reuse techniques. A very good book, Karma McClure. It is adding reuse to the system development process. We think that this particular book is more on the systems, systemic reuse. It is not talking about software reuse, which is qualifying the software engineering like in the earlier slide. Here it is qualifying the software engineering, life cycle, everything will start getting impacted by the potential of reuse. Here we think that much later we talk about systems, system development process. It facilitates a systemic reuse. Software reuse by Ivor Jacobson, Martin Griss, Patrick, this is more towards object oriented, that is this kind of a software engineering. That object orientedness is seen in reuse based, OOSE. So both are very good books, both are very good approaches. Right now we are not able to do so much on this. This is proving to be difficult. That's an intriguing factor. This is promising when we are talking about throwing out code bases systematically. What fit the systems view? A systemic approach is likely to tell us which code bases fit into providing a better application. We think that that is what is resulting in 48 hours, pick some code bases, put them together and make them, they become more systematic. They become more systemic in the way they are talking about. They were not originally intended to do that. If I give the full application from which the code base came, then I don't know, things may be difficult. While many companies justify their investment in object technology by citing productivity gains realized from systematic reuse, few have seen productivity increases. Software development economics don't generally justify reuse. Without reuse, why bother with object technology? So it is very unfortunate that we stopped highlighting reuse as one of the positives of object. We didn't pay much because the idea of objects caught on, UML happened, and last 20 years we are talking about a host of applications with a promise to increase on the complexity at a faster pace are trying out the object oriented. They are built on object oriented technology foundations. We don't have to be so clear or so very focused on one aspect of object oriented. It has come to stay. Nearly 2 decades ago, Electronic Data Systems performed an experiment in which they redeveloped a manufacturing system that was originally written in PL1. A team of Smalltalk programmers received the same specifications and test suites as the PL1 team had been given and proceeded to replicate the manufacturing system. The results were impressive. The original PL1 system consisted of over 265,000 source code lines requiring 152 staff months. The Smalltalk system has only 22,000 SLOC, required only 10 staff months, and it took only 3.5 calendar months. The productivity increase is very obvious. Again, this is not an instance of comparing languages. It is comparing an application where a language PL1 which did not support so much of reuse and structure, took so much of effort and time, and what gave us a fillip with reuse, productivity, systematic reuse of software components, we are able to showcase that. A Smalltalk system was very good. Even though these numbers may appear inflated for everyday developers, this was still powerful stuff. It's a good pointer. Well, we have been always saying that if an organization is so focused on doing a specific thing, if not in this iteration, next iteration they will find some reuse of at some level. One application is not enough. Reuse makes business sense when you are talking across applications, when you are talking across components. It made sense that developers should construct programs from pre-built components rather than handcrafting programs line by line. The electronics industry, which assembles new products from component catalogs, is often cited as the model the software industry should emulate. A decade later, we have reusable frameworks for creating user interfaces and reusable libraries for network communications and data storage, but few components for creating applications. In general, applications are still handcrafted. We certainly have not seen an order of magnitude of increase in productivity, and in fact we have been lucky to just get a few percentage points of annual productivity improvement. This remains an intrigue. It's not that we didn't have good designers, it's not that we didn't have people who cannot make things interoperable, but why didn't it scale? Scalability remains a very huge challenge in developing software applications. This scalability is not only in terms of machine scalability, but also in terms of people scalability. That is something which is essential, and what has solved the problem is a service-oriented architecture at that level of platform or an infrastructure or a software, that's cloud computing platforms. In fact, it has done more than scalability, it has talked about elasticity. Suddenly you need 30,000 machines more. Talk about cloud computing. We didn't anticipate that. Suddenly we need to have 15 servers. Talk about service-oriented architectures. It helps, that architecture helps, it has a positive. So to some extent, we are able to address the machine scalability. The physical machines are of no concern to me where they are. Let them be anywhere. There is a lot of spare capacity on the machines, and I can scale. Within 5 minutes, I will get access to 50,000 plus. So there was a wonderful experiment with which I was there associated with a launch of a mobile phone brand. They were measuring the footfalls. How many people thronged the stores world over when a launch of a mobile phone happened? A good challenging exercise. Now what was their next problem? How many people who were there looking at the wall where the mobile launch was announced very eagerly all over the world are likely to purchase the mobile? Well, I purchased. It was a Vivo brand, no prizes for guessing. It was a Vivo brand which came with a fantastic announcement, and cricketing brands were supported. A lot of things were happening. People were eagerly awaiting for that Vivo brand launch. It was the next week it will be in the market, 10 days. We were also following. So how many footfalls? How many of them will convert it into purchase? A few years back, hardly a few years back. Well, whether all those metrics are inflated, bloated, whether they are correct, whether we use the correct parameter to judge a footfall, these are difficult questions. It's a workable idea. Something happened, we did some exercise, appears to be all right in so many locations where we were able to track. It matches the physical estimate. Very difficult to estimate. You talk to a shop owner, he won't tell how many people were waiting in front. There used to be a case where the televisions were not in every home, and most of the television sets were on the display. So when crucial matches were happening, about 30 to 40 people were always in front of the shop. Not that they are going to purchase, but window shopping. They loved it because it's popularizing the television. If not today, tomorrow they will buy. 3 times they will go and stand in front of the shop. 4th time they would want to buy. Why people buy is a very good book. We need to understand certain things in a different manner, but they do it. So the point here is very simple. We talked about one, scalability being addressed. We talked about the way in which we can probably think of, as I said, better applications, complex applications which we didn't think of in terms of how many people roughly on a given day, so many people will come to a particular shop. This is what was the plus in systems. Systems people are always like that. How many users will come to your computer center? When is the frequency maximum? At what time? Systemic approach has always been welcomed in all these cases. Systemically we are through. Close to the lunch time, several people may want to go to the computing center. Now today we don't even take lunch. We are not even taking lunch. So like this, there are very good systemic methods of estimating what happens. Most mobile users play games while on the bed. They retire and then play computer games. Mobile games has that statistic. It is not that we did every case. Systemically a theory tells that it is like that. Most of them do that. Just before retiring for sleep, they like to play one mobile game and sleep. A good percentage of users. So systemic approaches have been proving to be a very nice way of justifying reuse and interoperability, and therefore productivity improvements. Typical reasons often given as to why we have not seen widespread systematic reuse in the software industry: you are using the wrong language, not invented here syndrome, lack of management support. This is now dwindling. This is now dwindling. Not invented here syndrome will haunt. Most software people are paranoid about anything. It's a paranoia that makes them live. A different kind of a paranoia. It makes them live. Otherwise it's not a good thing to happen. We have to find out when things will go wrong. So it's not invented here. This is not made here, this software. We know what is the software. We have the best of the brains in software and we are like this. Those people don't even compare to the best of the brains. Why should I believe that that piece of software is going to work? You are using the wrong language. This has been a concern. Choice of language. That's the reason why I spent some time in the earlier lecture on small talk. There is nothing like correct or wrong, but then each time when a choice of a language is made, it is proving to be wrong because we didn't get the success factor. Hardly 36% of the projects are successful. In postmortem, in retrospect, usually that point will be made. We did not choose a wrong language. Maybe had we chosen this language, in future if we have to do a similar kind of an application, we may have to use a different language. This point is very commonly aired. Our strategy, now we don't even have time for postmortem, lean life cycles, just about in time, just in time, and therefore what's happening is the idea of project is giving way to product. If it works, it works, otherwise throw it away, make a new one. That's how it is. What is reuse? If you ask 5 programmers what reuse is, you will get 8 different answers. It's not a joke, it's a fact. Till today we don't have a concrete idea about what exactly is software reuse outside of the lower level. I created this object, I know I can reuse it. It is usable in some other place. What we are talking about reuse is designed for reuse. Application level, system level, component level, we don't want to come down before that. But most programmers tend to mistake reuse as a few code segments. Square root, it's like a macro. Macro is reuse for many programmers. Earlier days when we were doing the machine language, we found that some functionalities appear very frequently. Square root is 1. So we created one macro called square root. The macro statement is given, the assembler will expand that macro into the code. You don't have to retype the machine language code so many times. give macro sqrt, the assembler will expand. The ideas were there, the ideas were always there, but then what we wanted to do was a higher level, a higher grade of reuse where the return on investment says yes, you do this like that. This distinguishes software reuse from software salvaging. Reusing software that was not designed to be reused. Many people regard salvaging as reuse because that is something which they do often. Something went wrong. How do we salvage? That is when we talk about software salvaging, in sense that, see, somebody has spent a lot of time, they didn't give good documentation, it was working for some time, suddenly something went wrong, we quarantined this piece of software, it is lying there. Can somebody work on it? Some of the projects which our students were given some years back was like that. What was normally called maintenance mode just got slightly refurbished and they started calling it software salvaging. Please see whether you can break that piece of software which is out of mode today. They are not using it, it's just there lying there. Break it down into some pieces. See what portion of it can be brought back, salvaged, call this a code segment, create a game like that. If you find 10 or 15 code segments, this nice salvaging. Otherwise we have spent a lot of money, we have spent a lot of time. It was good for some time, after that it became good for nothing. Now we don't know what to do, it is there, we can't even maintain because we don't know why we should spend time on maintaining, nobody is asking for it. So it is like that. So what we did is very simple, we started telling that you break it open, take it, get some simple small pieces, see what is that code base that can be brought into the loop again. Who knows, like this Microsoft Code Fun or like that code base integration which I have illustrated in one of the lectures, earlier lectures, they may put together and come up with a better application. The idea is good, software salvaging in open source, it happens always. Always it happens in the open source, reusing software that was not designed to be reused. So these are certain things which we have been talking about. Ideas are very simple. But in practice we should be very careful, because let us never forget what Bettenmeyer remarked, saying that how do you know that this line of code in software is not impacting the entire electricity supply that is also being operated on software control. One line of code that you are injecting in a piece of communication software may simply go ahead and then create havoc in your telephone exchange. So therefore we said that certain mission critical applications are all silos, watertight. We have to verify that they are secure. So we have been talking about choosing the pieces of software. We have been talking about many things. The BOSS software, CDAC was very nice. They developed this BOSS. How do you know there is no virus in it? Why will we certify? It's open source, we can go ahead and use. So these are all certain simple ideas that we have been talking about. This distinguishes software reuse from software salvaging. We are not talking about software salvaging. We are not talking about doing anything outside of designed to be reused. That is when software reuse is very attractive. These are ideas, they are not so attractive. Software reuse at a granularity where it is at least in the design phase, design for reuse is what we want to call reuse. There is no point in talking about different answers. One single answer, designed to be reused. You have to design to be reused. Thank you. We'll meet in the next lecture.